So we'll move on now. Fengzhou, I think you're online, so I think hopefully the internet issues are resolved. So presenting seismicity scanning based on navigated automatic phase picking SNAP.
Okay. So today I'm talking about the seismicity scanning based on a navigated automatic phase picking SNAP. The title here is actually a name of a system or a workflow for earthquake monitoring, which could automatically detect and locate earthquakes. So the goal of earthquake monitoring here, we know that earthquakes happen in lots of places, and actually the earthquakes are a very important way for us to know the underground structures and the tectonic activities of the underground world. So what we really need is a good earthquake catalog in order to know where and when the earthquake happens. So what we expect for the earthquake catalog, ideally it is comprehensive, like we have large and also the very tiny little small earthquakes in the catalog. And also we want it to be accurate in location, and also we don't want artifacts, meaning that false detections included in the earthquake catalog. Also, we want that this process to be efficient, the location process to be like real time, and finally, we want the earthquake catalog quality to be consistent throughout time. However, these four captures are not always possible in the catalog. For example, usually for the analyst to create the catalog, we can achieve the comprehensiveness and accuracy. However, it's really slow, and different analysts will create inconsistency of the catalog. And even if you stick to one person to do the catalog, it will be different in quality day by day. If it's tired or happy or angry, the working outcome will be different. On the other hand, if we use a computer system, we do it automatically. It could be real-time, efficient, and consistent in quality, but usually some of the tiny little small signals are missed in the computer system, so it's not as comprehensive, and sometimes the program makes some uncertainties and gives some false detections, thinking that some other signals might be earthquake, creating the inaccuracy. So what we really want to do here is make a more powerful computer system to earthquake monitoring and create earthquake catalog with more comprehensiveness and accuracy, as well as efficiency and consistency. So talking about earthquake location, I think many of you may think, oh, that's probably something like this. When we look at the station, we have P waves on the vertical channel and S waves on the horizontal channels. Then we zoom in to pick the P and S. Then we know from the station how far the earthquake is. We can draw a circle, and if we have multiple stations where the circles intersect in the location, that's the earthquake epicenter or hypocenter. So things are not this easy in the real world. Sometimes we have mistakes in phase picking part, or other things can be wrong, and the circles from some stations may not intersect all in the same place. So in the common usual computer system, this will lead to an overall fitting to all the data set. So this will lead to some uncertainties or mislocation of 10 to 20 kilometers in the catalog. So We do not want this. And this is a simple example, and we have more complex examples in earthquake location process. So this is an example. Here I show in different stations, we have very complicated waveforms, and you have multiple phases to peak. So in this case, we see 3 groups of phases, but you don't know which earthquake do these phases belong to. So we have different scenarios here. We can say, oh, this are the first, belong to the first earthquake, and that's the second earthquake. Or in a different scenario, we have the first earthquake, second earthquake, or third earthquake. And we have even more scenarios when we see a complex waveforms like this. This is what we call phase association ambiguity in earthquake location problem. And this is very common in aftershock sequences, induced seismicity, where the earthquakes happen clustered in both time and space, like 200 earthquakes in 1 hour. So they're really clustered. A few seconds, you can have 2 or 3 earthquakes. So now come to the solution. How do we probably can solve this problem? So in this method, in the first step, we kind of take a more general picture of the whole study area instead of diving in individual stations in the first place. We assume each place in the study area to be a potential source at each time. Then we can calculate the theoretical arrival time at each stations, and then stack the waveform segments of each stations. If you assume the place is correct, then you will find energy peaks in all stations, and you stack, you'll get a bright point like this. On the contrary, if you assume the point is incorrect, you will not get all the stations with the high energy segment. So the stacked value will be low. So in this way, we kind of create this energy map throughout time, and then you find the peak here. That's your approximate location of your earthquake. And then with this information, you can predict, you can like calculate the theoretical arrival times on each station. And you, in this case, now we know this earthquake signals belong to the first earthquake because we see a point here at that time. And then we see another patch, not showing here, later here. So we know that belongs to the second earthquake, and that's the third earthquake. And this is how we solved the phase association ambiguity. And that's why we have a navigation from the first step for the phase peaking. And in actual phase peaking, we use the kurtosis function to pick the exact phase here. So this is a seismogram. And when you calculate the kurtosis function, so it shows a sharp peak here. So that's where you want to pick the onset. And once you have all these P and S phases, you put it in the locating system. So this is kind of like the circles intersect here, and some circles do not intersect in this place. So instead of fitting overall all the data directly, we count the number of intersections at each point for a preliminary solution, and exclude the outliers. And finally, we then do the fitting to all the data set. So with the 3 steps, it's the how we solve the challenge and the phase association ambiguity in the earthquake location program. And now I show an application example in California Ridgecrest earthquakes. So the Southern California Earthquake Data Center catalog, automatic catalog, is more scattered, and we I think they include more false detections and inaccuracies in their catalog. And we actually find a good example here that the energy concentrated in this green spot, and that's our solution to this earthquake. Well, in their catalog, they have 2 red dots here as 2 artifact earthquakes that are shown in their catalog with 15 to like 30 to 40 kilometers away from the true source. So to conclude, we have developed this new method for automatic earthquake detection and location. It kind of become more comprehensive, but it's still not as good as human analysts. But its accuracy is really high with over 99.7% true positives in the test data set. And it's real time and it's consistent in catalog quality. The magnitude of completeness is 0.9 throughout the aftershock sequence of the Ridgecrest earthquake. So the current work is to improve more about the SNAP method. Hopefully we can achieve as good as the analyst in comprehensive to include more earthquake in the catalog. And finally, we can have a SNAP and the catalog is done. Thank you.
Okay, great. Thank you, Fengzhou. We have maybe a minute or 2 for questions before we move on to the last presentation of the session, this part of the session. I could just jump in. So the work for this is, like you were looking at an example in California. Are there any examples from British Columbia that are occurring with, you know, there's a kind of an increase in activity at Mount Meager with some tectonic and volcanic unrest? Are there any possibilities of using this in a Canadian context?
Oh yeah, actually, when this method was first developed, it's used in the induced seismicity site in the Alberta, and then it's used in British Columbia for generating a catalog. So this has a wide application potential with induced seismicity, aftershock sequence, and regular earthquake monitoring. Actually, there's an ongoing project in Vancouver Island in British Columbia to construct like 4 to 5 years long catalog, because it's too long for human to analyze the waveforms. So it could be useful.
Okay, thanks, Fengzhou.
Yeah, thank you.
So, Gilles, do you want to jump in with a quick question?
Thanks, Fengzhou. Very, very didactical presentation. Very appreciated for non-specialists like me. A question and a question to you and an answer to Brock. In EGP, we need to have a relation with environmental, resource development. So that's the reason it's applied to induce seismicity. Is there any in your system? Is there any big difference between natural earthquake and induced one in your sequence, or is it really the same processing?
That's actually a very hard question.
Sorry.
Well, first, it's really out of the scope of this study for method development, so for the physical processes, it's hard to say. We see similar signals, but sometimes it can be different. It's a very complex physical process, I have to say.
Okay.
Yeah.
No, and that's a very good answer. So yeah, okay. Thanks, Fengzhou.